Hello everyone. Am I audible? Okay. Okay. So good evening everyone. I think we can get started. Let me know if you face any issues with video or volume or anything like that. Okay. So this is the recap of the last class. So we just started some basic around operating system. So what we covered was computer organization. Again, this was very specific to the operating system. We did not study it from the computer organization per se, because that is a separate topic, and then you will learn that in a separate model anyway. Okay. But like we did look into what exactly is memory. Again, all of these things we learned from physical hardware perspective. So what is memory? Then we saw that there is a chip and there are this array and all that. So we understood what is an address, what is read write, what is address bus, what is data bus. Then we also had a superficial look at what is CPU, and then we understood what is fetch, decode, execute cycle. And then we a little bit touched upon interrupts also. So we saw what is hardware interrupts and what is software interrupts. So again, we'll do this again today because that is what we need for system. So this is what we did last time. So I just added one additional memory here, which is ROM, which is read-only memory. This is something that we will discuss at the end of the class when we actually go into how the system works. Okay. So this is read-only memory. Again, don't worry about it this much. We just added this block into yesterday's diagram, but we'll look into it at the end of the class. So any questions up to this one? From yesterday's class? Anything? So voice is not so clear. Is it? Can everybody hear me? Okay, I guess like maybe you have to check. Okay. So no questions. Can we move forward now? Okay. So again, like this is just a recap. Wait, there was a question. Codes run after referring IVT as system calls, right? Okay, so we did not say those are system calls. Those are interrupt service routines. System calls are something different. It is something same and it's also something different. We'll discuss that in detail today. But we do not call the code that is run after an interrupt as a system call. We call it interrupt service routine. Okay. So we call it interrupt service routine. Okay, so we'll do a quick recap of this anyway. So remember that how exactly we define this how exactly we define this interrupt service routine, right? So we had the CPU, which is some kind of a chip. Oh, my voice is still not clear, is it? Right. Wait a minute. Let me check my devices again.
Is it better now? Can everybody hear me now? Okay. Okay. Okay, let's continue now. Sorry about that. So now what we have seen last time is like we have CPU, which is basically some hardware chip. Again, note that we are completely into hardware up to this point. So, and it had some pin, which is basically literally a wire that is coming out of this chip, and it is connected to some bus, and then finally it is connected to some kind of a IO device right here. Right. So again, through physical wire, they are both connected. Again, there might be a circuit in between, we don't care, but some one way or the other, they are connected with one another, right? So whenever we saw example of keyboard, right? So whenever we press some key or something, what happens basically is that like this IO device sends a signal to CPU, signal in the sense like some pulse or something like this. It sends to this particular pin, and then CPU becomes aware that okay, some data is available from the keyboard, and now we should read it, right? So we also saw that with this signal, okay, let me do that. This is okay, I guess. Okay, with this signal, there is generally a number which is associated with this. We call it an interrupt number, right? We call it an INTR number. So INTR is short for interrupt. Okay, so we saw that like whenever keyboard there is a data available at the keyboard, it sends up a signal, and along with that signal, there is a number associated. We call it an interrupt number. So CPU has access to something known as a table. We call it an interrupt vector table. Okay. So here then we had this interrupt number 0, 1, 2 up to whatever is supported by the hardware. And then there is some kind of an memory address here. Address 1, address 2, address 3, so on and so forth. So whenever there is an interrupt, CPU reads this number and it checks this table. And here it has this address. This address is somewhere, address is basically address of the code that it should run. Code to be run. Then what it does is basically the CPU changes its program counter based on this particular address and start running that subroutine, or start running that particular program. And we call that program interrupt service routine, as we discussed last time, right? So note that in this case, we discussed this interrupt is basically generated by an external medium, which is basically keyboard. So you press some key and there was a explicit physical event that happened, and that basically created a signal. And because of that, some code was run, right? So additionally, you can also create an event via program itself. So it depends on, so IVT is inside CPU, right? It depends, right? Generally, it is placed in some predefined location in your memory. That is generally the case. I don't know how the recent hardware does it. In legacy hardware, there is some portion of the memory where it is a fixed portion of the memory that there it will always store the IVT table, right? But again, like that has been there for a very long time. Recent hardware might be doing it differently. So I don't know about recent hardware. Yeah. Okay, so you can create an event. We saw that it was created through an external medium, like you press a key on keyboard. So you can also create it via a program. So for example, there are some instructions that basically create an interrupt. So for example, one such instruction is INT 80. So it is just an instruction. Basically, CPU understands it. If CPU sees this instruction, so again, we go into fetch, decode, execute cycle, right? If CPU fetches this instruction and decodes it, CPU understands that this is an interrupt. Again, this is created via your program, not by any external medium like keyboard or something. CPU understand that this is an interrupt. And again, it will do the same thing. This is the interrupt number, by the way. INT80 is basically an interrupt number. Again, it will go here and it will check where is the 80. 80 is here, right? At this particular point, whatever is the address, it will run that. Okay. So basically, the mechanism is same. Once you get an interrupt, you go to the IVT, you read what address, where is the code for that interrupt is stored, and you basically run that, right? Irrespective of whether it has been generated through hardware over a pin or by software through this kinds of instruction. Again, this is not the only instruction to generate interrupts. There can be others also. So modern systems have many different ways of initiating interrupts, right? So there is another way an interrupt can occur. Additionally, whenever there is there is an exception. So exception, what we can say is like the program did something it was not supposed to. Again, a very naive example of this is basically divide by 0, right? For example, something like this. Again, this depend whether this is an exception or not depends on the system. But for for example sake, we will continue this. We'll see more interesting examples when we actually go into memory management or process management. Right? We'll get to that also. Okay. Again, like this is just one example, divide by 0. So generally what you see is a segmentation fault, right? That is kind of like an exception. So other example can be segmentation fault. So what you did basically, you have array of size 100 and you basically, this is your array int 100 maybe something like this. And you basically try to access 2000, right? Then basically this is illegal memory access, right? Then there is a segment, there is an exception. We call it segmentation fault. So everybody understand an exception? Okay. So when there are some exceptions, that are detected by hardware. So for example, if you try to divide it by 0, the ALU in CPU will detect that this is not valid, right? So some of these exceptions can be detected in hardware itself. So for example, if you try to divide something by 0, CPU can detect that, right? You should not divide it by 0. You can just basically that's the wrong input itself, and it will raise again. It will raise something like an interrupt again. Raise an interrupt. Right. Similar to that. So it's called raising an exception. Whenever there is something wrong that has been detected by the system, it raises an exception, right? And again, the operation is somewhat similar to this only. You have an exception number, you go to IVT, check whatever is there, and you execute that, right? So is that understood? So same IVT table can be used by hardware interrupts, software interrupts, and by exceptions, right? Okay, great. Okay, so this concludes what we had up to last class, that is interrupts and all. So now we also saw an example yesterday where we wanted to run this particular code, where we had basically a is equal to 1, b is equal to 2, and then we did c is equal to a plus b, right? We wanted to run this particular program last time, and we had no operating system whatsoever. So we had to do so many things. So we have to find the memory in the RAM. So like we have to find memory where we need this, where we need to put this code, right? Put the code. Then we have to update the program counter. Then it started running. Then after that, we wanted to run another program because we had 10 programs or something like that. Again, we don't know which one to run. So all those things were making our life very miserable, right? Because you had an hardware, and just to run a simple 3-line code, you have to do so many things, right? And that's what makes things very inconvenient. So nobody will buy a computer if they have to do all these things, right? So the first goal of the operating system is to make use of the hardware convenient for the user or application program. So when we say user, it's basically some application program running on behalf of user, right? So for example, when I'm like playing some song, it's just some MP3 player is running, right? That is the user program, right? Or application program, you can call it. Both of them are fine. So the goal of the operating system is to make sure that these programs can be run in a bit of a convenience on your hardware, right? And the second goal is that whatever hardware that you have or whatever resources that you have, that those should not be wasted. So for example, it should not happen that you have multiple CPUs, but you are only running one program at a time, right? So you have kind of like you have 3 CPU or like 4 CPUs and still running one program. So 3 of the CPUs are doing nothing. They are sitting idle, right? So this is basically CPU, and there are still other programs that could have run, but you are not running those. So this is basically underutilization of the system resources. So another goal of the operating system is that you have to make sure that the resources are used in an efficient manner, right? So these are kind of like a high level goals of an operating system, right? Again, like what do we mean by efficiently is again depends on what kind of needs the user has. So some of the needs can be like user wants to run some kind of a very big calculations, right? That is one kind of a user need. Other kind of user needs, like it requires so many memory operations like there are in databases, right? So based on whatever is the requirement of the user, again, the definition of this efficiency changes according to that. So at this point, we will not go any more details into it, but once we get into process management, you will understand what I mean by efficiency, right? If we are running a single program, then you don't need OS. So if you're buying a hardware just to run this particular single program, and after that you are not going to use your machine at all, then sure, you can go get away with operating system. Again, like that's not a good system anyway, right? So you just bought some computer for running some kind of addition, and after that it's not usable at all. It's like that. Oh yeah, obviously. So whoever is running this that particular code on the hardware has to know this operating system quite well. Oh, sorry, hardware quite well. He should know what are the registers in CPU, how is memory connected to the CPU, how should program counter should be updated, all those things it should be doing. Okay, is this okay? Okay. So I don't think the video has an issue from my side. So my network is quite okay. I think like maybe you should check once. Yeah. Okay. So again, like these are the resources the operating system has to manage. Like again, CPU, memory, secondary storage is basically your hard drive, and other IO devices like mouse, keyboard, and whatnot, right? Like whatever you have, joystick. And all. Okay. Okay. Now again, just now we discussed that if I just want to run a single program on a hardware, maybe I don't need operating system, right? But that's not what we want at all, right? Because that's not efficient anyway. So what we want is like I as a user have multiple programs that I want to run on the same hardware, right? So this is something that is, these are like a general requirements that we have. Right. So as a user, I bought this hardware, I paid so much money for it, I might want to run multiple programs on it, right? That is the first general requirement, right? Then second is that I have multiple programs now. Whatever hardware I have or whatever resources I have should be fairly used by different programs, right? So for example, I might run MS Paint while listening to a song, right? So MS Paint requires screen and what keyboard and whatnot, right? Mouse and all, while playing a song requires speakers and all, right? So there are these resources that are available to my system. It should be appropriately distributed across these programs, right? MS Paint, play a song, or there is a browser going on, or WhatsApp is, so I'm also running WhatsApp on my system and all that, right? All these things has to be considered, right? So this resource distribution has to be fair. So for example, no point in assigning a speaker to MS Paint, right? That's not a fair distribution in some sense, right? Is this point understood? So as a user, I first point is that as a user, I want to run multiple different types of programs, right? One can be MS Paint, one can be playing a song, some MP3 player, right? So among these programs, I want whatever resources I have in my system should be properly distributed or fairly distributed. So again, what do we mean by fair? Whatever is currently needed by the process should be assigned to that process. So for example, if I have a speaker, I should not assign speaker to MS Paint because MS Paint does not need a speaker, right? But MP3 player might. So it has to be, its resources has to be distributed in some fair manner. Again, what does this fair mean? Depends on the user. So in my case, I want, my fairness was this only. If MP3 player requires speaker, it should be given speaker first, right? And finally, there are some systems where there are multiple users to begin with. So these are like shared systems. So these corporate companies and all that have very, very big systems, and there are like 100 users, 200 users, which can at the same moment can connect to this system and do their jobs, right? Or clustered systems, right? Like shared. Another example is clusters, high performance clusters, and also where there are hundreds of users are attached to this system and they are running their programs in their own way, right? So these are some assumptions that we take into consideration while designing an operating system, right? So again, if we just relax all of this, it basically we will end up with a hardware and a single program. That's all we will have. And in that case, maybe we don't need an operating system, right? Because it's a one-time activity. We'll do all the things manually, and once it runs, it'll done. Okay. So operating system should ensure that all these operations run smoothly on your system, right? That is one of the again, you can say a goal of the operating system. Yeah, supporting all this cases is basically another goal of the operating system. Okay, any issues up to this one? Any problems? So let me see, there was a question here. Which of the following should be the primary goal of OS? Convenience, efficiency, portability, scalability. So generally, primary goal in most of the operating system is considered to be convenience, right? It doesn't mean that it should not be efficient or portable or scalable, right? Again, portability and scalability, we will not discuss it right now. We'll discuss it when the times come. But convenience is generally the primary goal of an operating system. Again, it's not always the case. Like there is always a trade-off between convenience and efficiency, right? Again, this will be much clearer when we go to memory management, right? So it is convenient to assign the entire memory to an user, but is it efficient? No, right? So there always has to be a balance between all these goals, right? You should not be focusing too much on convenience so that you are not doing things efficiently, and also you should not be focusing too much on efficiency so that the system is not very convenient to use, right? So always keep this in mind that these are like soft goals. It's not like that I want this and I want this, I will have both at the same time. It's very hard to achieve all the goals at the same time, right? I hope that answers the question. Okay, I'll answer that also. Okay, so can you explain what it means to fairness is subjective? Okay, I'll explain that again. Okay, so consider that so for example, I am one user, right? Let's say I am user one and I am running two programs, right? MS Paint and playing a song, right? And what I want is like speaker should be assigned to MP3 player and it should not be assigned to MS Paint, right? This is my notion of fairness. This is what I think is right, right? I think this is right. This is right, right? Okay, then there is user two. He's running some different programs. So for example, a video player and an MP3 player. So he's running some video and running some MP3 player, right? What he wants is like whenever he's running a video, MP3 player should not play a song. That's what he wants. Again, it's his notion of fairness. So when you are running these two programs simultaneously, your speaker should go to the video player and it should not go to MP3 player, right? And user 2 thinks that is fair according to her, right? So fairness in that sense is subjective. Since I am the owner of the system, I should be able to decide what is fair and what is not fair. If you are having your own system, then you are the boss. You will decide what is fair and what is not fair, right? Again, entire thing will be much clear when we get to priorities. When we get to process priorities, these things will be much clearer. But up to this point is basically like user should decide which resources should go to which particular program. That's what I meant. Is that okay? Okay. Let's get ahead. Okay, so now we, oh my God. Yeah, sorry. So now we get to the crux of the problem, right? So all these things that we are saying the operating system will do, we can also say that I'll write the code for it and I'll ask user to run that code, right? That is one way of looking at it, right? And that is somewhat sums up the entire operating system in some sense, right? But let's say we ask user to do it themselves. So all this operation, managing the hardware, managing the software, we ask user to do it themselves, right? So again, we saw this already. Most of the users are not experts in computers and do not understand how the hardware works, right? So they don't know how to do it. That is the first problem, right? Second problem is that they might know how to do it, but they can still make mistakes. That is obvious, right? Like not everybody is not correct all the time, right? Users do make mistakes. So we might want to run some code and we write something wrong in it and it basically just crashes your entire system, right? That was not your intention, but by mistake you crash the system. So for example, if you know malloc and all, anyway, we'll get to that later. So you just keep on consuming memory in your system and finally it basically crashes because you use the complete RAM of your system, right? Again, that was not intentional, but you made a mistake somehow that you could not catch right away, and because of that system went, right? That is the one problem, right? Another thing is like there are some users which are malicious. So for example, this hackers and attackers, right? Cyber attackers and all, they will deliberately do something so that system goes down. So for example, some random guy comes in and like he tries to access my system in a very very wrong manner, and then basically that crashes the system in the end, right? Right. And from operating system side, there is no way to identify which of these three cases are currently going on. So whether user is not an expert, he's a mature like he's a novice user for considering the operating system. That is the first part. Or whether the user may be an expert, but he by mistake he did something wrong. That is the second part. And then finally is like the user itself is not correct, right? So there is no way for a system to know which of these users it's currently dealing with, right? So the solution is like you never trust a user whatsoever. You assume that user doesn't know anything and you treat him like a kid, right? So basically like operating, that is how the entire take of the operating system. User doesn't know how to do stuff, right? And that's why we should always block user from doing anything critical, right? So for example, handling hardware. Again, when I say hardware, it encompasses everything. Again, CPU, there is CPU, there is memory, there is IO and everything. Handling hardware is critical for system operation because ultimately this is where your code runs, right? So now since you can't trust the user, You will not allow user to do any of this hardware operations. That is the crux of operating system, that you never trust user to do anything. User will tell you what he wants and operating system will do it on user's behalf, right? So basically crux is this. Instead of user doing everything, user will ask operating system to do some task, and operating system will perform that task for the user. Okay, so here if you see, what user can only do is request. He cannot do anything related to hardware or system resources on its own, but it can request operating system to do it for on his sake, right? So for him, operating system should be able to do it, and the operating system will perform that task, right? Now, operating system is basically some code written by experts, written by and basically again tested by experts. So again, I'm not saying that there will not be a mistake in operating system, but most likely it will not fail, right? So this code you can trust, this person you cannot trust. And now we have basically created a barrier in between. So anything that is very critical for system operations, only the operating system will be able to do it, since this particular piece of code is written by highly expert engineers or researchers, and it has been tested by experts also, right? So this is a trustworthy code. User, you may or may not trust. No, I did not design OS. That's a very difficult task. So I did not. Any doubt up to this point? Any doubt why we can't trust user? Okay. Just 1 minute. Let me move. And basically, this is why we have what we call as dual mode of operations, right? So there is a user mode. In this user mode, only the non-critical tasks can be done. So for example, addition, subtraction, multiplication, division, or some like move, then you have to move some variables from variables from A to B or something like that, right? So all these operations will be in user mode. So for example, in our current example, right, we had this A is equal to 1, B is equal to 2, C is equal to A plus B. So this is a memory operation. This is again a memory operation. This is a computation plus memory operation, right? So all these things will be done in user mode. Note that this is not critical for system operations. This is something that user wants to do for his or her own task, which is not critical for system operations, right? So then question is, what is critical for system operations? Finding the memory to run the program, right? The initial issue that we had, where should I put my program, right? Where should I put my program in memory, right? That was a critical operation, because if you do this wrong, you might affect other program. You might override other program, right? Or you might delete some part of other program. So this is a critical operation. Again, another critical option is what should be the value of program counter. So what should be the value of program counter? Again, that is a critical operation, because it will from the next fetch decode execute cycle, it will start running that particular code. So what code should be run next is a critical operation also, right? Similarly, IO handling, right? How should we interact with keyboard and mouse, right? And mouse. So all those things are critical, and those should happen in operating system only. So that is what we call as kernel mode. So by the way, when we say operating system, you can also say that this is basically somewhat kernel, right? Operating system code is basically kernel code. It's just the nomenclature. Okay. I hope this is clear. Yeah, correct. So isn't kernel in the layer of some again that depends on the operating system design. So the question is that isn't the kernel is the layer in the operating system? Again, that depends on the design of the operating system. Some operating systems, what we call as like monolithic kernel, where it's basically a big, very, very, very big code where entire thing has to be done in the operating system only. Okay, so again, when we say kernel, so it depends on the operating system. What do we mean by that? Some operating systems provide a lot of features, maybe not sure, should not say all the features. So we saw what are the basic features that operating system should provide, right? The resource management and all, but it can do much, much more than that, right? So many features. Again, this is not a very concrete definition. It is just for sake of explanation, right? Many features, and thus has a big kernel. Again, big when I say the code size is very large. Okay, so this is what we call as monolithic kernels. Again, this is not like the exact definition of monolithic kernel, but this is just for sake of example. Then there are something known as microkernels, something like that. I don't remember exactly, but I think they are called microkernels, where they provide bare minimum support. So they only provide read, write, reading a file, writing a file, then creating a process, creating threads and all that, right? Memory management. So bare minimum features. Everything else you can do it as an add-ons. Okay. So again, this is not required for what we are going to study right now, but this is just somehow this is one way of differentiating different types of kernels, right? But in most of the operating system literature, when we say kernel, it's generally we are talking about operating system only. And when we say operating system, we are generally talking about kernel only. Right. If there is a distinction between that, I'll make it clear. But from this point onwards, whenever I say kernel, we just assume that it's operating system unless I specify it differently. Is this okay? There is another question. OS code is stored in memory. Can we fetch its file from memory through some user program? Okay, so the question is basically this. So when operating system is running, its code is stored in memory because everything has to be done through fetch, decode, execute cycle, right? It means the operating system will also has to be fetch, decode, and execute. It means the code has to be there in the RAM or main memory. Now the question is, can we read it through? So generally they don't allow it. User programs cannot even touch operating systems. In general, user programs can't touch operating systems. Okay. Yeah, monolithic is monolithic is the type of kernel. Yes, monolithic is a type of kernel. Again, this is not very critical at this point, right? Can we switch between two modes? Is it in user's hand? Okay, so we'll get to that. Switching between the modes, I'll get to that. Okay. Anything else? So how do they lock OS code? That is something that we will study in memory management. Okay, don't worry about it right now. We'll cover that in memory management. How do we lock it, right? It's not that easy. So I cannot explain it right away because it will require a very significant background. By the time we reach memory management, you will have the necessary information and then we will discuss this again. How exactly operating system blocks the user process from accessing its memory, right? So we will discuss that later. At this moment, just assume that it can. Okay. If user tries to do it anyway, you get an exception. Okay, going forward. Now the question is, we say that we can't trust users, so we have decided that there will be two modes. In one mode, only these kinds of operations will be provided or supported, like addition, subtraction, and moving data across different memory locations and all. In other mode, it will do some critical observation, something like this. So finally, who will be doing this? Who will be executing anything? So ultimately, whenever we say something is getting run or something is getting executed, CPU does that. CPU is the hardware component which actually performs all the computation and executions, right? So, so when we say user mode, it's actually, we say that CPU is running some program in user mode, right? Because when we say user is running addition, it's actually CPU running the addition on behalf of user, right? So when we say user mode, we actually say that it actually means that CPU is in the user. So let me be clear on that. So ultimately, or maybe in the end, CPU runs all the code in system. When CPU is in user mode, it is running some user program. Okay. When CPU is in kernel mode, it is running OS code or OS program. Again, program or code, whatever. Okay. So when CPU is in kernel mode, it is running the OS code. And then again, it means it can perform critical task. Is this understood? Just 1 minute. Somebody is at the door. Hey, sorry. So there are a few questions. Let me just check again. Yeah, so question is that how does the CPU knows when to execute OS or user mode? That we'll get to. After this slide, we will actually get the explanation for that only. Once you enter the user mode, then OS code doesn't run anymore. Correct. So if you are in user mode, you cannot run OS code. That is the case. That is correct. So we'll get the details in next slide only. So any issues in this particular slide? So when we say user mode, it's actually, we are saying that CPU is in user mode. When we say kernel mode, it actually means that CPU is in kernel mode. Okay. Now wait, running the OS code means the OS is also itself is some code, right? So OS is also in some sense a code, right? Not in some sense, it is a code, right? When for performing all this management operation, you have to write the code, right? So the OS experts and researchers, they have written that code, right? And the CPU will execute that code. That's what we mean by running OS code. So operating system itself is a software, right? Keep that in mind. OS is a software. Okay. So whenever I say running OS code, it means the code that is written for this OS software that is getting run. Anyway, so now the question is, now we have defined that there are some instructions that should be only be run in kernel mode. Some of the things should not be run in user mode. How does the system know? How does the system knows whether whether some instruction that is run by user is correct or not? Right. So we have to do the checking now, right? So whenever an instruction is ran or executed, by the CPU, it needs to check if it is in user mode or kernel mode. Okay, so whenever an instruction is executed by the user, the CPU needs to check whether it is in user mode or kernel mode. And if it is in user mode, if here CPU needs to check if instruction is allowed. So for example, if the user can still run these instructions, right? It still has access to those instructions for handling hardware or performing memory management and whatnot, right? So if user tries to run that code, then CPU needs to know that this is not valid, right? So what it needs to check is that user is not running something that is not allowed. If user is running something that is not allowed, then there is an issue, right? So then at every instruction, it has to run this check, whether it is allowed or not, whether it is allowed or not. If this is, I am currently in user mode, whether this instruction is allowed or not. If I am in kernel mode anyway, everything is allowed. So if it is in user mode, it has to check whether this particular instruction is allowed or not, right? So this check can be done in hardware because it's faster. This check is done in hardware since it's faster. Yeah, so question is, isn't user code required to run OS code? I don't think so. So maybe I did not understand your question correctly. So are you saying that can there be a user program which does not invoke user OS code? Then yes, there can be. There can be, yes. In modern operating system, no, there isn't, because you have to create processes and you have to kill processes. So that always requires OSSL. But in a very, very pathological cases, there can be, right? Again, modern operating system, you don't have any user program that does not have any operating system interface or operating system support. You cannot create a process itself without operating system. So in real life, it's not the case. Yeah, virtualization we won't be covering right now. It's some different topic. We'll cover it later. Because again, for understanding virtualization, you need to understand abstraction. And to understand abstraction, you first have to understand processes. Then only the entire thing makes sense. Okay, so you understand that, right? This check has to be done in hardware because it's faster. That's it. Right. Any doubt in this? Okay. Yeah, so the way to do this in hardware is basically we add an additional bit. So again, bit is like basically a binary variable that we add. It can be either 0 or 1. This is present in the hardware itself. So it's generally present in the CPU only, right? So if CPU is in user mode, then the mode bit is 1. If CPU is in kernel mode, then the mode bit is 0. If mode is equal to 0, then system, when I say again system, in this case from context, it's basically CPU. Okay. When if mode is equal to 0, then CPU is in kernel mode. And if mode is equal to 1, then it is in user mode. Okay. And now we will come to the point that we need some mechanism to switch between the two. So the design we are following is basically this: user program request a task from OS. All right, this was the design that you started with. OS executes the task. Okay. So this is basically mode 0. Whatever execution happens here in operating system is basically mode 0. And here you have mode 1. So when the user performs a request, right? Whenever it performs a request, there has to be a transition from mode 1 to mode 0. Because once the OS code starts running, it has to be in mode 0. Okay. So there has to be a mechanism such that this transition can happen, right? This is understood, right? How does the transition will happen? We'll get to that. But the need of this transition is clear, right? Okay. And once the OS completes the task, it has to return also. So again, you have to change this mode from 0 to 1. Right. Whenever the OS execution of the task completes, it has to go back to the user mode and it has to go to 0 to 1. I never said that OS code is always working. I don't think it's always working. It depends on the design, right? It may be running, it may not be running, right? I don't know. It depends on the design. Generally, operating systems are event driven, so I don't know. The way the designers of the operating system choose to implement it depends on that. It might be running, it may not be running. Right. So there is an alternative question: is OS code always in memory? So there is a difference between having code in memory and code getting executed, right? So you can have, so this is your basically your RAM. Somewhere here, so this is your RAM. Somewhere here is basically your OS code. And you have CPU here, right? And it's basically doing again fetch, decode, execute. So it is running, it can fetch, decode, execute any code, right? Need not to be OS code. It can be running this particular code as well. There is some code here, some program. It might be running this code also. We don't know, right? So is it OS always running in this case? If I only have a CPU which is running some program, is the OS is being run? No, right? It's not running. So it's not getting executed right away. It's not always running, but it's always there in the memory. So there is some portion of your RAM where the OS will always be there. Okay, so if that's what you are asking, then yes. Okay, now let's understand how exactly this bit transition happens. So that happens through something known as system calls. Okay, so again, we need a mechanism for this. User program should be able to request some kind of a task from operating system. To achieve this, system call is a mechanism for that. Maybe I should change the color. It's basically a mechanism so that the users can request some tasks from the operating system. Again, like this explanation is basically same only. So we have blocked user from doing some certain task, and like instead the user requests operating system to perform those tasks, right? And these tasks will have to run in privileged instruction. So again, privilege instruction is basically the critical instruction that we were talking about. Okay. And the mechanism to do that is basically system call. And again, we have to change the mode here. When we say change the mode, it's basically the mode bit. We have to change that. Right. And that happens to interrupts. So change in mode bit happens via interrupts. Now, in this specific case of system calls, it happens to software interrupts. Or they are called as traps also. Right. Again, this is a feature that has been there in hardware. So this particular software interrupts or like this traps is something, a feature that is given by the hardware only. Okay. So whenever user wants to request some service from the operating system, it will initiate a software interrupt. And whenever a software interrupt is encountered by the CPU, it will change the mode in hardware directly. Right. So this basically means that whenever there is an interrupt operation, the bit mode changes to 0. Whenever the CPU gets an interrupt, the bit mode changes. Okay, and this happens in hardware. So we already saw that interrupt service routines and everything is actually controlled in hardware itself, right? Right. It gets a signal either through program or through exception or through hardware, whatnot, right? And then basically it goes into IVT and checks for the interrupt service routing, right? So whenever that operation is going on, it will also set this particular bit to 0, right? Is this understood? Yeah, so this diagram is from Galvin only. So why OS code isn't in read-only memory, and so that we can't modify it? Yeah, basically you as a user, you should not modify OS code, right? That is one basic necessity, right? Because we don't trust the users. That's the entire point of operating system. We don't trust the user to do anything. So we can't allow user to touch the operating system. But that's why it's not modifiable by the user or not cannot be written by the user. So how is the mode version? Are all the assets running in kernel mode? Precisely, right? So it happens in hardware. Again, this is an old design. I don't know what about. Okay, I'll explain it again. So I'll draw the diagram. So consider that you have a CPU here, right? And here somewhere is the mode bit. This is your mode bit. Assume that it's currently in user mode, right? So for us, mode bit equal to 1 means it's in user mode, right? So what happens right now is there is an interrupt that comes in. There is an interrupt that comes in to the CPU, right? Now, whenever interrupt comes in, CPU has to suspend its fetch decode execute cycle, right? You have to stop the fetch decode execute cycle. Whenever interrupt comes in, CPU stops fetch decode execute, right? Right, and goes to IVT. Goes to IVT and runs the interrupt service routine. Again, based on the interrupt number. This is something that we already saw, right? On top of this, whenever it sees an interrupt, it will also set the bit to 1. So addition to this, addition to all of this, in addition, CPU will also set mode equal to 0. Okay, so it happens in hardware. So this mode equal to 0 happens in hardware whenever there is an interrupt. So basically, while performing these operations, going to IVT and getting that address and all, it will basically set the mode as well. Is that clear now? What basically means is that all interrupts are running in privilege mode or kernel mode. That's what it means. Yeah. Okay. That's what it means. Again, this is an old architecture, right? In recent architecture, there can be additional ways of changing this bit, but in legacy architectures, this is how they do it. Through interrupt, they change it, right? Again, this interrupt can be anything, right? So this interrupt can be anything like hardware interrupt and all that. But currently, what we are interested in right now is basically trap, which is a software interrupt. It can be any other interrupt, but we are currently interested in software interrupts, right? I hope this is clear now. Okay. So here, if you see here, it is showing trap, right? So this is basically a software interrupt, and whenever there is a trap, it automatically sets it to 0, and then basically then it goes to IVT, and then in IVT it also has a number, right? So trap will also have a number. Then it will go to the interrupt service routine, and interrupt service routine will finally tell how exactly the request should be handled. So the question is, all system calls are interrupt, like user program making requests for output on monitor? Yes. But they are special type of interrupts. They are software interrupts. Yeah, so we'll get to that. So I have not yet discussed how exactly the system call code is running, right? I have just discussed that how to change the mode. I just hope that everybody understood this. If not, I'll discuss it again. No, so in kernel mode, no, not hardware interrupt, right? That's what I'm saying. Kernel mode, you get into kernel mode whenever there is a trap or there is an interrupt. That's all I said. I'm not said any type of interrupt. I'm just said like if there is an interrupt, the hardware will automatically set the bit to 1. Okay. That's all I said. Shall I explain it again? Okay. Okay, let's start from the basics again and understand what we try to do, right? So, okay, let's start from what we want to do, right? So what is our goal? Our goal is that we want to separate user execution from OS execution. So user execution means like whatever the user program that is running, and OS execution is basically the operating system code, right? We want to separate these two. And the reason for that is basically, why do we want to do this? Because we do not trust the user. Okay, so that is why we say that we want to keep clear separation between, okay, this is something that operating system should do. These are the tasks that operating system should do, and these are the tasks the OS should do, right? This is the separation that we want. This is our goal, right? To achieve this, again, to achieve this, we introduced two modes, right? The first one was user mode and second one was kernel mode. Okay, and we said that whenever some user program is running and it's not running some critical operations, we say that CPU is in the user mode. That's what we said, right? And we said that whenever there is some critical operation going on, which generally happens in operating systems only, CPU is in kernel mode, right? So what this basically means, right? When CPU is in kernel mode, it can perform all tasks, all allowed tasks or whatever, right? So all instructions it can run. So operating system has entire control your hardware, right? It can run whatever code it wants. Okay, but that can only possible if it's in a kernel mode. The CPU whenever CPU is in kernel mode, it can run whatever code it can, right? So there is no restriction here. Is this understood? Okay. So this was our motivation and this was our initial solution design for that. Now the question is, now the problem is user can still try to perform some critical task or maybe run some critical instruction, right? So the user can still run some code which basically tries to do this critical task, right? Because why that is the case? Because we don't trust user. That is the basis of all of this. So we don't assume that user is a nice guy, he will never do something bad, right? He can still try to run it accidentally or deliberately, right? So when these things happen, then the question was, if this thing happens, how to avoid this? Right? How should we stop user from running something that it is not supposed to run, right? That was the question. So to do this, what we said that whenever CPU will check before running an instruction, maybe I'll write it in different way. Before running an instruction, CPU will check it's allowed for a current mode. Okay, so if CPU is currently in user mode, it will check whether the instruction that it is about to run is allowed or not, right? So some instructions we said are not allowed in user mode, so it has to check every time. Whenever it's running something, it first has to check whether this particular instruction should be run in user mode or not. Is this point clear? Is this point clear? Okay, so first let me tell you an example of this critical instruction. One critical instruction is basically changing the program counter. So we saw that program counter decides which program to run from the next fetch decode execute cycle. So changing the value of the program counter is a critical instruction, right? User should not be allowed to do that. So when I say this changing the program counter, it's basically boils down to context switch. Again, there can be program counter updates in different settings like function call or something, but in this case, it's basically what we are calling it context switch. Again, these details will get to that in the process management, but this is basically a critical instruction. Performing a context switch is a critical instruction. User should not be allowed to perform context switch. Only operating system is allowed to perform context switch. Okay, so this is, again, we'll discuss it later in the class. All these things is just an example. The details will get clearer once we move forward, right? User should not be allowed to do that. Only operating system should be allowed to do that. Okay. Any doubt up to this point? Let me check the questions also. So kernel mode is basically OS mode only. Correct. Kernel mode is basically OS mode. So that's what I said, right? Whenever I say kernel or OS is basically the same thing unless I say otherwise, right? That's it. The programs we write and execute all happens in user mode. Many of the operations that are there in our programs happen in user mode. Some of the operations which are specifically dealing with the hardware occur in kernel mode. For example, if you want to read an input from your keyboard and if you want to display something on your monitor, that is basically dealing with hardware, right? That happens through system. That basically happens in kernel mode. Writing to the screen or reading from the keyboard happens in kernel mode. But if you are just moving one data from one variable to the another, it is basically some program level operation. It does not happen in kernel mode. It happens in user mode. So when you are writing something, if it is getting displayed on the system, again, you are dealing with the hardware, then it's in kernel mode. Again, this changing the user font and all, it's a little bit tricky because it actually deals with something known as shell or user interface, right? User interfaces can generally be an application program. Again, depends on the operating system. So for example, in Linux, user interfaces are application programs, while in Windows, I guess it's a kernel subsystem, right? Again, we don't know. Depends on the operating system. So if it's a user program, then changing font is a user level operation, right? While running non-privileged instruction, does it always have to switch to? No, no, no. So in privilege mode, you can run anything you want. Once you are in kernel mode or privilege mode, you can run any instruction you want. You don't have to change to user mode to run something. You have access to the entire set of instructions. Only in user mode, you only have access to a subset of instructions. Yeah, so once you are in privilege mode, you can run any instruction you want. That is the same question. While running non-privileged instruction, does it always have to switch to user mode? No. So if you are in privilege mode or kernel mode, you can run any instruction that you want. Yeah. So again, this context which I'll discuss in detail when we actually go to program manager. Okay. So yeah, printf. I will discuss printf in some time. Correct. There is a write system call. I will discuss printf in some time. Okay. But yeah, the malloc will result into changing the kernel mode. That depends on how malloc is implemented. Generally, it does. It calls this brk system call. That is, again, there is in memory management, not up to this point. Any doubt in this concept though? What we are trying to do here? Why do we need to switch and why not? Any doubt in that? All the topics that their questions are from some future topics that are not very interesting right now. But any issues in this up to this point? Okay, let's move forward then. Okay, so we just saw that we are discussing this diagram, right? So whenever user wants to do some kind of operation, it has to do through the system call, and we have to change the bit to 0 or the kernel one, right? So to achieve this, it has to use this software interest that we are calling traps, right? So now let us just see a very small example. Let's say you want to print something on the monitor, right? Okay. Printing to monitor. Okay. So you have some message. Some hello world message is there, and you want to print this to the monitor, right? So for doing this, what you will do is like you will call a software interrupt or a trap. You call a trap for some system call. So again, you pass in some number here, right? You basically call and you pass in that you want to print, right? So you are at this particular position. You are running a user program, and the user program is for printing something. Now, once you have your message ready, which is hello world, you have to tell operating system that you want to print this thing to your monitor, right? So for that, you need a system call. So then here you call that particular trap for whatever is required for the print. You call that particular trap. Then it will create an interrupt. It will basically create an interrupt to CPU, right? Once this happens, CPU will basically go to IVT, and from this it will basically pick up the interrupt service routine. This part is clear, right? So here the application program or user initiates a trap saying that it wants to print something onto the screen, right? So it adds all these details somewhere, and it says that this is what I want to do, and I am initiating this particular trap. So this is basically your system call. Once user initiates that, here you will set the mode to 0. This happens in hardware. Then basically you get an interrupt to CPU, then it goes to IVT, then it basically finds the interrupt service routine and it starts executing. So here, this is basically operating system code or kernel code. The interrupt service routine basically has operating system code, and it knows how to print code for printing to operating system code for printing to screen or monitor. It is already stored in that interrupt service routine, right? Then it basically performs the hardware operation, and then it basically does a return. Here you do the return. Once this printing is done, it basically returns to user. Here again, and whenever it returns, there is an instruction which sets the mode back to 1. Calls an instruction okay. So this is how it happens. So question is this: from user mode to kernel mode, CPU need interrupts to change the mode bit. But what happens when we need to move from kernel mode to user mode? Does it require to interrupt to do so? No. So there is a specific instruction for that. Okay, to change, to set the mode bit to 1. Again, when we say 1, it is basically user mode. There is a specific instruction. So there is a specific instruction. The operating system will call that instruction before returning to the user. Okay. So operating system will call that instruction. The instruction will be set mode to 0 or set mode to 1. That will be some kind of instruction like that will be there, and operating system will call it. So OS calls the instruction before returning from the system call. So operating system code will call that instruction. And that instruction will set bit mode to 1. I hope that is clear. Any doubt in that? Is this clear? Okay. If anybody has any doubt, please post it on the chat. Okay. Fine. So for example, here, right, this particular part of code is what we are discussing, right? This particular part of the code is what we are discussing. So there is an instruction to set this bit to 1, and it will basically return back to the user, and so on. So if you see all the critical operations that happen, all those happen with mode is equal to 0, and the only code that runs at that time is basically kernel code. Okay. And that's how we achieve this separation between user and kernel, right? So we don't allow user to run any critical operations. If he wants to do something, it has to be done through system calls. Okay, so let's go forward. If you have any doubt, please write it onto the chat box. I will discuss that. So again, these system calls that are there, right? Those are very low level instructions. So system calls are very low level in the sense that you still need quite of expertise to actually call these functions or initiate a system call. Low level methods and require expertise. So even calling a system call requires a very significant level of expertise, right? So I'll share this link with you guys anyway. So I have an example ready here, right? So this is some web page that I found out. This is how you call a system. I hope my screen is visible. This is how you actually initiate a system call, which is quite bizarre, right? You don't know what RAX is, RDI is, whatnot, right? So it's very high level, like very low level data that you need to understand to even initiate a system call, right? So the trap that we are discussing, this particular instruction is basically that trap. I hope this is visible. This is visible, right? Yeah. So again, this code doesn't make sense, right? We don't know what this is, right? Some random stuff is going on. And if you are writing some program, if you have to write this, it's not very convenient, right? And that is one of the goals of operating system to begin with, that provides some convenience, right? So what people have done is basically, instead of writing this, they have wrote another code on top of this. So what we call it as a wrapper code or a library code, right? So on top of the system call, what they provide is a C library code, right? So what basically you have is actually printf. So you call printf with some arguments. The printf ultimately will call this code, this particular code. In the end, the printf will call this particular code, right? But for you, you don't have to worry about what exactly does this mean, right? You only know how to understand how printf works, like how you should pass arguments to printf, right? That's all you need to know, right? So that this is how they actually provide this support for this system calls. They actually provide it through some library, intermediate library, as shown over here, right? Okay. Yeah. So printf is not a system call. the code of printf ultimately will make a system call in the end. So printf itself is not a system call. Similarly, that malloc, somebody say malloc, right, or scanf, right, those are not system calls. Those are library functions, and those library functions will ultimately initiate the system calls to the operating system, and that makes your life easier, right? Because you don't have to understand what this gibberish is, right? What is this, right? Like we don't literally some assembly code that we don't understand, right? So to make your life easier, there are some people who actually help you out by writing this system library functions. Okay, I hope this is clear. Whatever, right? Like depends on this. Okay, I think we'll get this in some time. Maybe we should look at the questions first. Oh, these are just some questions, right? Can you guys answer this? So question is this: what events cause a processor to switch from unprivileged execution mode to privileged execution mode? Now, when we say unprivileged execution mode, it basically means user mode. And when we say privileged execution mode, it basically means kernel mode. So question is, what events cause a processor to, again, when we say processor, it's basically CPU. These are synonyms, okay? What events cause a processor to switch from unprivileged mode to privileged mode, right? And the question is again, what events cause processors to switch from privileged mode to unprivileged mode, right? Is the question understood? Yeah. Okay. Let us see the answer. Yeah. So again, interrupts, exception, and system calls. This is all the things that we discussed, right? We say hardware interrupts, we said exceptions, and when system calls. So when we were discussing the interrupts as a whole, these are the things that we discuss anyway, right? Right. And now second is this: returning from an interrupt, exception, or system call causes execution mode to switch from privileged mode to the unprivileged mode. So we saw that there is a special instruction, right? This particular special instruction, the operating system will call this instruction before it returns to the user back, right? So that is what it's discussed here, right? When we are returning from operating system code back to the user, it will cause that instruction will cause the bits to be set to 1 again. Is this clear? Yeah, this is again one question, right? This also we discussed today only. So the question is, when a regular process is running on single CPU, all of the following are true except. So kernel is not running. So we discussed this, right? We saw that diagram where we had this memory, and we said that this is OS code is here. Somebody asked this question also, and then there is some program here, and your CPU is here, and it's basically running this code, right? So we saw that the OS was in memory, but it was not running. The process was running. So this is definitely correct. Again, this can be writing again. This is called as IO. So this is something that we have not discussed yet. So okay, so let me discuss that in a bit here. So IO operations. So IO operations for now, assume that this is basically writing to some hard drive, right? Something like that, right? You are writing to the hard drive, are very slow. Again, because there is a latency, right? You have to write it from your CPU to whatever you have, right? From hardware or something, right? It's very slow. So what generally happens what generally happens is they run in background. So how do they run in background? There is a separate hardware for that. There is a separate hardware for that. We'll discuss that later, right? Yeah. There is a DMA hardware, right? Yeah, correct. But thing is that it runs in background, right? Because it's slow. So the thing is that if you keep CPU waiting while this IO operation completes, the entire thing will be very, very slow. So if, because it takes, let's say, like around 1 second to write to your hard drive, and your CPU will be waiting for 1 second while this operation completes, right? And it will not be doing anything. That is not optimal. So generally these things happen in background. So this is again correct. Again, CPU will generate an exception, a software interrupt, if certain addresses are accessed. Yeah, right. So again, we saw the system calls and all, right? In the program execution, it can call a software interrupt, right? A program itself can call a software interrupt, right? So only thing that we are sure is definitely not going to happen is that CPU is in the supervised mode, because we have this dual mode of operation. Is this correct? Is this understood? Yeah, supervisor means again kernel mode. So let's write it down. Kernel mode is equal to supervisor mode is equal to privileged mode. Okay, pardon my spelling. So kernel mode is equal to supervisor mode is equal to privileged mode, and user mode is equal to unprivileged mode, right? Or non-supervisor mode. That's it. They are basically, it's a synonyms for one another. Is this understood? Wait. Here it is saying that CPU is always in supervisor mode, so it's false. Correct. So whenever you are running a user process, right? So there is a regular process. So whenever it's a regular process, it basically means user. Whenever it's running in user process, it cannot be in supervisor mode, right? Because we know that user cannot be in kernel mode. That is the basics of the operating system in the first place. We don't trust users, right? Is this understood? Okay. Okay, so here this is the catch, right? You have a single CPU, right? That is the first thing you understand, right? So this is something we already saw. You have a single CPU, and on a single CPU, only one program can run at a time, right? Because there is only one fetch decode execute cycle, right? Yeah. So on single CPU means there can be multiple CPUs. Yes. So again, I deliberately did not bring that up because that will that will add additional complexity at this point. So when we get to the processes, there we will understand that there can be multiple CPUs also. So when you say you have 8 cores, right? 8 core CPU, it means there are 8 CPUs actually. Your system has 8 CPUs or 8 cores. Multi-core systems basically means that multi-core CPUs, right? Multiple CPUs, right? So you only have one CPU now, and your operating system is there somewhere in the memory here. But what we are given is that a regular process is running. Basically, this CPU is running some other code except operating system, some other code, some user process. So now, since there is only one CPU, only one code can run at a time, right? And it is given that it is running regular process code. So that basically means that it's not running OS code, right? Since there can be only one code that run at a time, and the code currently being run is user code, so it cannot be operating system code. Is this understood? Okay, great. So again, I'll explain this also, but do you guys have any guesses? Okay, there is C, there is B. Okay, C. Most of you guys are C, saying C. Okay. So answer is C. I will explain why that is the case, right? So note that when we when we use a system call, it is generally to perform a critical task. Okay, and one of the critical tasks is, for example, writing to a file, or instead of saying writing to a file, writing to hard drive, right? So this here it says write to a file, which is basically equivalent to writing to hard drive, which is basically equivalent to performing IO operation, right? Which we know is critical. Is this understood? So when we say write to a file, it basically means writing to the hard drive, which basically means we are doing an IO operation. And whenever there is hardware involved, it has to be done through. Okay, I'll explain it again, right? So when we say writing to a file, right? When we say write to a file, the file is usually stored on a hard drive. Hard drive. This is understood, right? So you open some file on your system, it is generally there in some of the drive, right? C drive, E drive, whatever drive, right? Secondary storage. Yeah, why not? We will get to that. First, let's clear out C. We'll get to that. Other options we'll get to that. But everybody understood why writing to a file is basically an hardware operation? Okay, right. So when it means you are dealing with another IO operation, right? So there is an IO operation involved in this, and which is basically hardware operation involved in this, right? So whenever you want to do anything related to IO, you are not allowed to do that because operating system does not trust you, right? So it has to be done through a system call. Is this understood? Whenever you are performing an operation with some hardware, it has to be done through operating system because it's a critical operation. Anybody has doubt in this? Somebody asked the question to explain again. Is this clear now? Okay. So that's why it has to be done through system call. Okay. Is there any doubt in this particular point? So this we have covered. Is there any doubt in this particular point? So this is basically memory operations. And again, we saw if it's just a memory operation, and this memory is it's basically the program's memory, right? Program memory operation. So global variable are program variables. So if you are doing something within the program, it should be good enough, right? Is it not clear? Shall I explain it again? Okay. So you are doing basically program operations. So it is basically clear, right? So now there is third part, which is called the user return function, right? So user return function. So user return function is part of the program. Is this understood? If you write a function, it will be part of your program. Is this clear? This is understood, right? And what you do when you call that function, you are basically, you this is what you want. You want CPU to execute some part of the same program. Okay, so it's your code. Your program was, CPU was running your program in any way, but when you do a function call, you're just telling CPU that okay, now run this part of your program only. Is this understood? When you do a function call, the CPU will execute your program only some different part of your program. It was running main function, now it is running foo function, some other function, right? Foo bar, whatever function, right? But the function is still part of your program itself. Is this understood? Okay. So yeah, I'll get to that. Wasn't PC must be updated. So there are I'll get to that. So that PC part, I'll get to that, right? But anyway, this you understood, right? Okay. This means that you are in the same program. So you are not doing anything, you are in the same program and not performing anything that affects others. So it's basically what we are trying to say is that whenever we do a function call, you basically running some code which is in your control itself, and it has nothing to do with other programs. That's all we want to say, right? In this sense, it's not critical. In this particular sense, it's not critical. In this particular sense, it's not critical. Okay. So basically doing this operation, you don't need help from the kernel, right? For this operations, you don't need, since everything is in your control only, and since whatever you are doing is not going to affect any other program, it's basically not critical. And that's why it does not require kernel help. So it's basically saying that we don't need a system call here. Printf is a function call, but ultimately inside printf there is a system call. Printf is a function call, right? But in the end, you finally have to print it to the screen, right? That requires hardware support. So that's why in the question they have specifically mentioned user return function. That's why they have specifically said that. And now we'll come to this. How do you say? So now we'll come to this program counter thing, right? So everybody understood this, right? If you are just having user return function, you're basically not touching any other program. So it's basically you don't need OSS help, right? So now we'll get to this part, right? Program counter. So there are multiple cases where program counter changes. First case, this we already saw. When we start a new program. So when we start executing a new program, we have to change the program counter, right? So there was some old program which was already running. Then you have to start a new program. Is this understood? I hope this is understood. So this is basically operation. This operation is between programs. So multiple programs are involved in this operation, right? Okay, there are one program was there before. Now there is a new program. So you have to manage both of these two programs, right? So if you change the program counter in this particular case, there are multiple programs involved in your system, right? And there's a bunch of other operations. We'll get to that in next class. This is understood, right? This is okay? Yeah. So here in this case, since multiple programs are involved, this is critical. Okay. When we change the program counter for this particular purpose, it is critical because multiple programs are involved, right? Okay. Is this understood? And the instruction to achieve this. So this is basically what you're saying. One program has terminated or one program was running and now you are running another program. There is an instruction to achieve this thing. There is an instruction which allows you to achieve this thing. Okay. I don't recall it exactly. I guess it's called schedule instruction. It's a shared instruction, right? Okay, so this involves multiple cores. So you have to call this schedule instruction. Then it will pass the control to operating system, and the operating system will do all these things. Note that here you are changing the program counter, but it is between processes. That is the main crucial part here. I hope this is clear. Now in second case, when you do a function call, here also you have to change the program counter, right? Obviously, right? Because whatever you want to execute has to be there in the program counter, right? This is understood, right? In this case also you change the program counter, but here only current process is involved. Right. Here only current process is involved. A program is involved. Is this understood? Let's call it program. So there is no multiple programs involved here. There was some program which was running, and again, when you do a function call, it is the same program that is running, right? In that sense, it does not affect other programs, right? Is this understood? And since it is isolated to this particular program, it does not require OS help, right? So there is an instruction to perform a function call also. The instruction which performs a function call is called call. So if you see the instructions for changing program counter here and program counter here are different because their purposes are different. This is switching between two different programs, and this is just calling a function within the same program. So the instructions to achieve these two tasks are different. Here it is schedule and here it is call. So again, I'm not perfectly sure about the schedule, but there is some instruction for this. But here it is definitely call instructions. Okay. So here the operation is within a process itself. It does not affect other programs. Here it can affect other programs because you are doing operation between two programs. So here you need operating system. Here you do not need operating system. Is this clear? Well, let me check. There were a few questions, I guess. So modify global variables mean changing the memory content which need memory write call. Doesn't this need? Again, like I said, right? Memory, it's a memory operation. Memory operation and also to the global variables of the same program. So you're writing to the memory of the same program. That is not a privileged operation, right? So we discussed this when we actually defined user and kernel boards, right? Some time back. Here, right? Reading and writing to into the program's memory. This we already defined, right? Global variables come under program memory. So if you are writing those, it basically means that you don't have to involve kernel in this thing, right? So you don't need a system call here. Okay. Okay. So any doubt up to this point? Okay. So only one part is pending in this is again, this was also somewhat like an introductory class only. Only part that is pending right now is basically how does a system starts, right? I think we can discuss this in next lecture and then we'll go to process management. I think there was a hand raised. Oh,
Hello.
hey, hi.
Hi, sir. Sir, due to lag in my internet, I am unable to understand frame number 36. Can you explain once, sir?
Okay, I'll explain again, right? So, so basically, the question was like, whenever we do a function call, right? That means we will be changing program counter there, right? In that case, right? So if we are changing program counter, is that not a privilege operation, right? Should we not involve OS in that? That was the question, right? So what I said is like there are different scenarios where you will want to change program counters, right? So one scenario was that there is a new program that you want to run, and there is some program which is already running, right? In that case, if you want to run the new program, you have to change the program counter, right? Based on whatever is the new program location. I think that is understood, right? In this particular case, where there is one program that is new program that you want to run, you have to change the program counter accordingly. But note that here in this particular operation, there are multiple programs involved. So there was some program which was already running, and now you have a new program. So there are at least two programs involved in this operation, right? Is this understood?
Yes, sir.
Now, when there are multiple programs involved, it's basically means that there is a management problem here, right? You have to manage these two programs simultaneously, right? So operating system, you need operating system help for that. Whenever there are multiple programs, you basically need operating system help for that, right? So for this kind of program counter change, this has to be done through operating system. Okay. So this is what we call as scheduling or context switching. We'll study this in the next class. Okay. In second case, when you do a function call, you are basically asking CPU to execute some other part of your program, right? Instead of so here there is only one program involved. It is just some other part of the program which you want your CPU to run. That's it, right? Since there is only one process involved here in this case, you don't have to worry about operating system here, because this is some operation which is very specific to that program itself, and it does not affect other programs. Yeah. So in this case, you don't need operating system. So basically you don't need a system call. Question is, program counter takes the address value of the instruction of that particular address from the memory. Can you clarify it? Sorry, I don't understand it properly. So maybe this will help you, right? Like, so this is how exactly your program looks like when it is in memory, right? So it's basically these instructions: instruction 1, instruction 2, instruction 3, instruction 4, right? So whenever you write a function, again, it is stored somewhere in this particular format only, and it has an address. So this is the start function address, right? So global start is basically, this is one function. There will be another function. There will be another 1, 2 functions, right? So when you say call and that address, it will basically update the program counter accordingly. So let me just see, takes address of the program for of that instruction. Correct. So program counter takes the address of the program of that instruction in the memory. Correct. That's exactly what it does. So it's basically when you do this, right? So I think you guys know function pointers, right? From C. Yeah. So let's say you have this function, right? Like void foo, void this and this, right? So you already saw that like this foo is basically some address, right? Address to the code, right? So when you call this function, so if from some other, so let's say from main, from int main, again whatever, you call this function like this, right? You basically call this function like this, right? So it is basically equivalent to, so if this gets converted into this particular instruction, call foo. Okay, this is basically equivalent to this. So call is the machine instruction and foo is the address, right? So you say call this particular address. This is how the function call works. There are some other stuff like stack and all that we don't care about, but in principle this is how it works. When you say call and this particular address, the program counter will get updated accordingly. So now the program counter will get address of code or address of the function, right? Right. Whichever address the foo points to, program counter will get that address, right? Again, this is a local operation in the sense that you are calling a function which is there in the same program. It's in the same program, right? So it will not affect other processes or other programs, right? So that's why you don't need a system call here in this case. I hope this is clear. Correct. The program counter will keep updating with the number of different function calls. That is correct. Okay. Yeah. Anything else? After once the instruction complete, the program counter add to 1. Yeah, so that is fetch, decode, execute, right? We saw that it always perform fetch, decode, execute, and next time it does +1 to the program counter. That we already saw. Okay then. Yeah, we'll discuss this boot operating system boot up tomorrow, and like then we go to process management. If you have any additional doubts, we'll discuss in at the start of tomorrow's class. Okay.